Hello everyone. Yeah, so in the previous lecture, we were discussing the joint probability distribution, right? And then we have done their part, and then we were solving this example that the joint density function is given, and you have to find the some probability. And then we have already solved this example that p of x greater than 1 and y less than 2, right? So three more things we have. Let us do the other thing also. Right. So what is that probability? The second one, p of x less than y. So p of x less than y means what? That your density function was given as this one, 2e power minus x minus 2y, and 0 less x less infinity, 0 less y less infinity. Now you have to get the probability of x is less than y. Now this is the concept of multiple integral. You have to involve that. If you involve x limit in terms of y, then y limit can be 0 to infinity, right? We can do in that way. So you take a x limit is that involve x limit is up to y. So y limit must be 0 to infinity then. Actually it is minus infinity to infinity, but y value runs from 0 to infinity. So y is a will have 0 general limit, and x limit is up to y. But x starts from 0 and it will go up to y. And then it is fxy, that means the density function, dx dy. Now you put the value, we'll get the answer 0 to infinity, and x is equal to 0 to y, 2e power minus x e power minus 2y. I just separate them out, and I wanted to do dx first and then dy. So you have written this, and if you calculate it, the value will be 2 into 0 to infinity, that is the y value, and x we are doing integration, so e to the power minus 2y can be outside, and e power minus x dx, so it is equal e to the power minus x by minus 1 0 to y, and outside there will be dy. So this is again 2 into 0 to infinity. If you just simplify it, it will be e to the power minus y and minus of this plus 1 into e to the power minus 2y dy. Correct. And after that, if you just simplify it again, this is 2 times, because this minus was because there was one minus sign in the denominator, that I have taken. And then if we do it, it is basically 0 to infinity, e to the power minus 2y minus e to the power minus 3y into dy. And again, then we can do the integration, 2 into e power minus 2y by minus 2, 0 to infinity, minus 2 times e power minus 3y by minus 3 integration 0 to infinity. And if you put the value, this will become that plus 1 and this minus and plus, so plus 1, this will become 1, because 0 minus 0 plus 1 if you put the limit, and then minus 2 times it is minus 0 plus 1 by 3, 2 into 1 by 3. Just if you simplify, you will be getting that. So 1 minus 2 by 3, the answer is 1 by 3 for this integral. I hope you understood. And if you calculate the probability of this one, the same way we can do p of x less than a. Maybe I'll do it here if it is possible. Now p of x less than a, from the joint, how we can do? It is basically the marginal density, right? Marginal distribution function you have to get. So this one, the part C, we can do it as p of x less than a is actually p of x less than a comma y less than infinity, and that means x value is from y value is up to that and x value is up to a. So maybe I'll do it y integration first. 0 to infinity, and x is equal to 0 to a, fxy, so 2 into e power minus x, e power minus 2y into dx dy. And this integration, if you do, we can just separate them out. E to the power minus 2y integration, if you do, so e to the power minus 2y by minus 2, and 0 to infinity into 2 was outside, I'll take 2 is outside, into e power minus x by minus 1 and 0 to a. And if you put this integration, this limit value, so this e power minus infinity will gives you 0, so plus 1, so the first part is 1 because minus 2 and plus 2 will be cancelled out, so this part is 1 times 1 minus e power minus a, right? So 1 into 1 minus e power minus a. So the answer for this part is 1 minus e power minus a. And the last part is, the D part is the joint distribution function. How to get the joint distribution function? If you have f of ab value is equal to 0, if you have a lesser equal to 0 and b lesser equal to 0, right? And if you have a, like I'll show you the answer. So if your a and b value, both of them are less or equal to 0, f of ab value is 0. Whenever one of them is 0, because the value is 0, right? So f of xy value is 0, so that means this is 0. Whenever your a and b value is greater than 0, then the joint cumulative distribution function fab is equal to minus infinity to a for x, minus infinity to b for y. So this is x value, this is y value, fxy dy. And the same way, if you calculate the integral, you will be getting this. I hope this is clear. Okay. So now I wanted to do one that independent random variable, right? So what is that? So the independent random variables for any two sets A and B, if you have P of x belong to A, comma y belong to B is equal to their individual probability product, that P of x belong to A into P of y belongs to A. Then we say that the random variable x and y are independent. Now how can you relate with your independent event? If you remember that the event A and B are said to be independent, if we have P of A intersection B is equal to P of A into P of B. Remember? Now we said that these two are the intersection, x belong to A, comma y belong to B means x belongs to A intersection y belongs to B. And if that is equal to their individual probability product, then we say that the random variables x and y are independent. Clear? And then we have some equivalent result. We have some equivalent result. What are they? So for the case of a this probability, if the x and y are independent random variable, then that is equal to their individual probabilities product, right? Similarly, the cumulative distribution function, joint cumulative distribution function is equal to their individual probability distribution function product if x and y are independent variable, independent random variable. Similarly, if x and y are discrete type independent random variable, then their joint probability mass function is equal to their individual marginal probability mass functions product. If x and y are continuous random variable and they are independent, then their probability density function, that means joint probability density function, must be equal to their marginal probability density functions product, right? And whenever that x and y are not independent, we call them as dependent random variable. This is a very easy concept. We can easily check that something is, some two random variables are dependent or independent depending on the problem. Like look at this problem. The joint probability mass function of two discrete random variable x and y are given in this tabular form. We have already seen this problem, right? Now, are these x and y are independent? How do we check? First, we have to calculate the marginal, right? So, what is given here? Here, p of x is equal to I, comma y equal to j is given for all these boxes. So, x for x takes the value 0, 1, 2, 3, y takes the value 0, 1, 2, 3. We can calculate the marginal, right? So, how to calculate the marginal mass function? So, you just have to add up one more column for this table and one more row for this table, and then add up, then add them up, right? And in this case, p of x is equal to I, this will give, and this one will give you p of y equal to j. So that means x is equal to 0. If you just do the sum over this row, we'll get p of x is equal to 0. So what is that value? If I do the sum, it is 84 by 220. We have already done this problem in the last example, right? In the last class. This is 108 by 220. This is 27 by 220. And this one is 1 by 220. So this will gives you the marginal probability mass function of x. And similarly, column wise, if you do the sum, you'll get the marginal probability mass function of y, which is 56 by 220. Then 112 divided by 220. This is 48 divided by 220. And this is 4 by 220. Right? And now, how can you show that whether they are dependent or independent? Let us check one of the example first. We have to check all. This should be equal to, if I have this probability into p of y equal to j. That means they are marginal things. If you have these things, then we can say that x and y are independent. So let us check one by one. Check the first one first. So p of small p of 0, 0. It means p of x is equal to 0, comma y equal to 0. But from the table, what is this value? So this is this value. It is 10 by 220. Now what is the marginal of x is equal to 0? Now p of x of 0. It is that we have already calculated 84 by 220. What is marginal of y 0? It is 56 by 220. And we can easily see that this value is not equal to p of x is equal to 0 into p of y equal to 0. So the first step itself, we have understood that, okay, this is not equal. What we can declare from that? That we can immediately say that x and y are not independent. These two random variables are not independent, right? So if the first step, suppose you got the first steps are equal, then you have to check all boxes. If all boxes are that p00 is equal to that, that means for all values of I and j, if you get these things is happening, you can, then only you can declare that x and y are independent. Otherwise, if you see that in one step that they are not equal, you can immediately declare that they are not independent. I hope you understood. Okay, so this one we have done. Yeah, this is the whole table that I have shown you. Just you might take a snap of it to finish the problem, and then this is the rest of the problem that we have already discussed. Now we have one more example related to the continuous random variable. So the joint probability distribution function is given for the random variable x and y, which is of this form fxy. Are x and y are independent? We have to answer it. So to check whether two continuous random variables are independent or not, where density function is given, joint density function, we have to find their marginal density function, right? So how to get it? So for x greater than 0, we have that marginal density function of x is fxa. How do you calculate? We have to keep x as fixed and do the integration over y, right? The whole sum. So it is integration, y value is 0 to infinity, fxy into dy. X you have to take fixed, do the integration over y. But this value is actually 0 to infinity e power minus of x plus y into dy. So I can immediately take e power minus x out, and then e power minus y dy, that's integration value is e power minus y divided by minus 1, and limit is 0 to infinity. And if you put the limit value, it is basically e power minus x into 0 plus 1. So it is e power minus x. And if your x value is less than 0, anyway that fxy value is 0. And therefore we got the marginal density function of x is fxx is equal to e power minus x whenever 0 less than x less than infinity and equal to 0 otherwise. Now the same way, can't we find the marginal density function of y? Yes, so the marginal density function of y is, I can get it the same way, which is fy of y is equal to e power minus y whenever 0 less than y less than infinity and equal to 0 otherwise. We got it. And then finally what we got, we have f of xy is equal to e power minus x plus y. It is equal to e power minus x into e power minus y, which is equal to fxx into fyy. I can write whenever you have 0 less than x less than whenever you have 0 less than x comma y less than infinity, and if there are otherwise cases all these are 0, so we can immediately write, and therefore we can declare that this is x and y are independent random variable. X and y are independent because their joint probability density function is equal to their individual marginal density functions product. So these are x and y are independent random variable. Independent random. I hope it is clear. Okay. Now I have another good example which is related to the discrete type random variable only. Now suppose that n plus m independent trials having a common probability of success p are performed. So n plus m independent trials, all of these trials have the common probability of success which is p. Now given that, let x be the number of success in the first n trials, y be the number of success in the last m trials, and z be the number of success in the total number of n plus m number of trials. Then the first question is, are x and y are independent? So try to realize that what is this x? X is the number of success in the first n trials, where each trials have probability of success is p. Right? So is it not x is a binomial NP variable? Right? So we have x is a binomial NP random variable. So with parameter number of trial is n and probability of success is p. So therefore we can write it as binomial NP random variable. At the same way, y is the number of success in the next m trials. So y is also a binomial, right? But where y number of trials is m, but probability of success is p. So y is also like that. And what about z? According to this definition, z is the number of success in n plus m number trial. So z is also a binomial random variable with number of trials is n plus m and where probability of success is p. So these things is given. Now you have to calculate that, you have to check that whether x and y are independent or not. So then for that we need to find the joint probability distribution, joint probability mass function, right? So we have to calculate the probability of this event. Probability of x is equal to I, comma y equal to j. But what this event means? That it means that in the first m trial you should have I number of success, and in the second m trials you should have j number of success out of n plus m number of trials. So what is this probability then? So how many ways that I number of success you can get out of n trials? NCI ways, right? And probability of in the same way we can have MCJ into probability how many total number of success you are getting basically. It is I plus j number of, so p to the power I plus j, and others must be the failure. But what is the probability of failure? It is 1 minus p. But total number of success was n plus m. I plus j are the success, so the failure number is n plus m minus I minus j. So you have written this one. Now can I not write this is equal to NCI into, I just divide this part p to the power I into this part also I can divide 1 minus p whole to the power n minus I. Can I not write this one into probability of into this value mcj p to the power j into 1 minus p whole to the power m minus j? I can write this. But what is this? Is it not the probability mass function of x is equal to I? So this is actually p of x is equal to I into this is actually p of y equal to j. So this probability mass function, joint probability mass function is equal to the individual marginal probability mass functions product. For which value? For all 1 less or equal to I less or equal to n and 1 less or equal to j less or equal to m. And therefore we can declare that x and y are independent random variable, independent random variables. Now we have one more example, one more question. Are x and z are independent? How do you calculate this part? Okay, let's see. Again, recall that x is the number of success in the first n trials, y is the number of success in the m trials, next n trials, and z is the number of success in the n plus m number of trials. Right? You need to calculate whether x and z are independent or not. But how do you calculate? Okay, let us see. So we observe that is it not z equal to x plus y basically? Z is actually x plus y, na? X plus y is what? In total n plus 1 m number of trials, you have I plus j number of success. It counts the total number of success, I plus j. So z is actually x plus y. Now if I want to calculate probability of x is equal to I comma y equal to j. So sorry, not y, z equal to j. If you want to calculate this value, can I write this as p of x is equal to I and z value is x minus j, x plus y. So therefore we can write it as y in terms of y and z minus x, but z value is j and x value is already I. So can I write this as y equal to j minus I? Because z equal to x plus y, these are the same value, meaning, but we have already seen that x and y are independent. We have already seen that x and y are independent. So I can write this as x is equal to I and y equal to j minus I. This is basically x is equal to I into p of y equal to j minus I. How? Because x and y are independent randomly. So I can write it as NCI into p to the power I 1 minus p whole to the power n minus I. This one I can write it as MC j minus I p to the power j minus I into 1 minus p to the power m minus j minus I. And if you just simplify all this value, so I can write it as NCI times MC j minus I p to the power j, because I plus j minus I, so p to the power j into 1 minus p to the power n minus I plus m minus j plus I. So I can write it as n plus m minus j. N plus m minus j. For which values? For all the values of I less or equal to n, and j values runs from I onwards to up to what? N plus m. Whereas the individual probabilities are what? P of x is equal to I. We already know this. Individual probabilities is NCI p to the power I 1 minus p whole to the power n minus I. And P of z equal to j is what? P of z equal to j is n plus m tj p to the power j 1 minus b whole to the power n plus m minus j. And we can calculate that this value is actually not equal to this value p of x is equal to I comma z equal to j. This is actually not equal to p of x is equal to I into p of z equal to j. Just put I equal to 1 and j equal to 1. If take a particular value, we can immediately see no, they are not equal, right? And therefore we can declare that x and z are not dependent, whereas x and y was independent, right? So we can declare that x and z are not independent. I hope you understand. Okay, we have one more example. Yeah, this one we have already done. We have one more example. How do we solve it? Let x, y, and z be independent and uniformly distributed over 0, 1. Then compute x is greater than or equal to z. So here three independent random variables are there. All of them are independent and uniformly distributed. So we know that what is the multi-density function of uniformly distributed random variable? You have to calculate p of x greater or equal to y. Now because x, y, and z are independent, so their joint probability mass function, which you denoted by maybe f x comma y comma z, xyz. We can say it as xyz. That means the joint probability density function of xyz. And that should be equal to their individual probability density function. So marginal density function fyy into fzz. But all these x, y, z are uniformly distributed over 0, 1. That means what is their density function? 1 by 1 minus 0. So basically 1. So all of them values is 1 into 1 into 1. So this value will be actually 1. And what is the range? Whereas the x range is from 0 less than x less or equal to 1, 0 less or equal to y less or equal to 1, 0 less or equal to z less or equal to 1. And otherwise this value is 0. So this is the density function we got, joint density function. Now you have to calculate the probability of x is greater than or equal to yz. So what we can do again, then we have to involve the triple integral. How we will do it? So if you take the limits of x as in terms of y and z, and y and z limit can be the general one, so between 0 to 1. And x is value will start from yz to x value is maximum value is 1. So we'll do this integration as, so x limit is starting from yz up to yx maximum limit is anyway 1, whereas y limit is general 1, 0 to 1, z limit is also 0 to 1, general limit, then fxyz dx dy dz, right? So I should write xyz dx dy and dz. But this fxyz value is 1, so I can write it as 0 to 1 equal to 0 to 1 is z equal to, and x is equal to yz to 1 dx dy dz, because this value is 1. Now if you do the integration, this integration is x from yz to 1, then dy dz is outside. So if I put the limit value, it is 0 to 1, y is also 0 to 1, 1 minus yz into dy dz. Next we do the integration for y, we'll be getting this value is 0 to 1, and y in terms of y we are doing the integration, so 1 y minus z into y square by 2 between 0 to 1 dz. If I put the limit, it is 1 minus z by 2. If I put the limit, it is 1 minus z by 2. So integration 0 to 1, 1 minus z by 2 dz. And after simplification, we'll get this value is z, that means 1 minus z square by 4. So 1 minus 1 by 4, this value is actually 3 by 4. We'll get the answer in this way for this example. I have one more example to show you. X is given as the Bernoulli random variable with probability of success is P, and Y is again a Bernoulli random variable with probability of success is Q. Right? You have to find the joint probability mass function and joint cumulative distribution function of X and Y. But because X and Y are independent, so we can immediately write P of that xy of x comma y is equal to that small x comma y, right? This is the small x. We can write that P of x comma y, that joint probability mass function at the value xy is equal to P of x is equal to x times P of y equal to y, because they are independent, right? And then we know that Bernoulli random variable takes values 0 and 1. If it is success, then it is 1. If it is failure, then we will take 0. Then this probability mass function will have 4 different values: P of xy 0 0, P of xy 0 1, 1 0, and 1 1. So P of xy 0 0 means what? That x will have failure and y is also having failure. What is that probability? It is 1 minus p times 1 minus q. Similarly, P of xy 0 1 means what? X is having failure, y is having success. So it is 1 minus p times success of this means this probability is q. Y probability of success for y is q. At the same way, xy 1 0 is what? It is p into 1 minus q, and p of xy 1 1 value is what? This value is must be p into q. So we got the probability mass function, and if you just write them together, we should be able to get right in this way, that x is equal to 0, y equal to 0, this value, x is equal to 0, y equal to 1, this value, x equal to 1, y equal to 0, this value, and x and y both are 1, is this value, and equal to 0 otherwise. So the joint probability mass function of x and y is given by this. Your next term is you have to also find the joint cumulative distribution function. Right? How do you calculate the joint cumulative distribution function? We have different cases. Right? How do you calculate? Maybe I'll just show you the answers. We are running out of time. When I have both x and y are less than 0, then definitely fxy, the cumulative distribution function is 0. Joint cumulative distribution. And then, because we have all possible cases, we have to take all kind of combinations also. Whenever x value is between this, for all possible cases, whenever x value is lies between 0 and 1, and y is also lies between 0 and 1. In this case, fxy is what? You will have x and y will take only the value 0 and 0. Now, what is this probability? It is 1 minus p q into 1 minus q. We have already done. But if you have x value is up to 1, 0 to 1, and y value is greater equal to 1, what will happen in this case? So p of x is equal to 0 and y value is less or equal to y, right? But y greater equal to 1 means y will take the value 0 and 1 both. So therefore, this is equal to sum of p of x equal to 0, comma y equal to 0, and p of x equal to 0, y equal to 1. So both the things. And both of their probability we know. We will calculate and we will get this. At the same way, if I take x value is greater equal to 1 and 0 less or equal to or less than 1, then what will happen? That y will take up to 0 value, but x will have two values, 0 and 1 both. So we'll have this probability. This is the sum. Again, we know this individual probability, we'll be getting this answer. And the last case is if we have x greater equal to 1 and y is also greater equal to 1. Now, without calculating also, you should be able to answer it. Because in this case, it is the total probability. And we know that this value is actually gives you the 1. But even if you calculate it, x and y both will take both the values. Right? That x value is up to, x will take 0 0 and 1, x will take 0, y is also taking 0, x is taking 1, y. So all possible 4 combinations. So we have to do their sum, and this value is actually 1. So without calculating also, we should be able to say that this value is 1. And if we just write it in a final version of the joint cumulative distribution function of xy, it is that. I hope you enjoyed the video. I hope these videos are helpful. In the next class, we'll come up with a new point. Thank you very much. We'll meet in the next video.